You know how time works. Cause comes before effect. A teacup falls off a table, it shatters, and you sweep up the pieces. You have never seen those fragments leap off the floor and rebuild the cup. To our senses, the forward flow of time is undeniable. Yet the core mathematics of the universe suggests this experience is a local hallucination. The foundational equations of reality, from Newton's laws of motion to Maxwell's electromagnetism and Einstein's relativity, share a jarring property. They are time-symmetric. Run these equations forward, and they describe the world we see. Run them backward, and they work just as perfectly. The math doesn't break. It doesn't even notice a difference. This leads to a conclusion that shatters our intuition. Time, at its most basic level, has no preferred direction. If the laws of physics are indifferent to time, why does the teacup stay broken? Our only clue is entropy, the second law of thermodynamics. It states disorder naturally grows. A whole cup is ordered, a million shards are disordered. But entropy functions as a statistical law, describing the most probable behavior of trillions of particles. It is a matter of overwhelming likelihood, rather than a hard, fundamental requirement of the universe. Because it is a game of probability, given enough time, it is mathematically possible for a shattered object to spontaneously and perfectly reassemble. We simply haven't seen it happen because the odds are so absurdly low. This chart shows the universe's entropy since the beginning. We experience forward time only because reality started in a low entropy state at the Big Bang. We are coasting on that order. Every forward moment is just a slow descent into chaos. Our experience of time is a temporary side effect of an accident 13.8 billion years ago. Eventually, that momentum will run out, and time will stop having a direction altogether. Because time isn't the rigid line we think, general relativity allows for a terrifying geometric possibility: closed time-like curves, paths through spacetime that loop back on themselves. In 1949, physicist Kurt Gödel proved that these loops are mathematically valid solutions to Einstein's field equations. In a looping universe, the past is reachable. If these loops exist, they create a breakdown of logic known as the Bootstrap paradox. Imagine a time traveler hands Beethoven the completed sheet music for the Fifth Symphony before he ever wrote it. Beethoven performs it, history records it, and the time traveler later learns it from a record, carrying it back to close the circle. Who composed it? The math suggests that information can simply exist without an origin point. Physics allows for objects and knowledge to be uncaused, effectively bootstrapping themselves into existence. To protect the logic of the universe, some physicists point to the Novikov self-consistency principle. It argues that if you travel in a loop, you can only do things that have already happened. The universe prevents you from creating a contradiction, forcing you to fulfill the existing timeline. If the timeline is a fixed loop, then your choices are already made. In such a universe, free will is mathematically forbidden. You are simply a passenger in a sequence that cannot be changed. We have seen that time is a statistical accident, and causality is a fragile loop. The world you see is built on a foundation of impossible paradoxes. This leaves us with one final assumption: that the physical, three-dimensional space you occupy is actually real. But even that is being questioned. In Part 2, we'll explore the evidence suggesting our world is a two-dimensional projection and the statistical probability that you are living inside a simulation. The nature of your reality is about to get much stranger. Subscribe now and watch Part 2 to see the proof that the universe isn't what you think it is. Part 1 explored how quantum mechanics challenges the stability of matter and forces a total reconsideration of how information is stored. Now we pull back. Leaving the microscopic behind brings us to the macro-scale domain of general relativity. In this framework, the mathematics describes a cosmos in a constant, accelerating state of growth. Decades of observational data confirm that the distance between galaxies is increasing every second. This leads to a difficult question. If the universe is expanding, what volume is it expanding into? Physicists have spent a century attempting to map the edge of reality. Their findings suggest the difficulty lies in the human mind's inability to model a state of true nothingness. Human intuition relies on the concept of nested containers, rooms inside houses, planets inside galaxies. We instinctively search for a box large enough to hold the universe itself. The simulation hypothesis addresses this bias by treating reality as software. In 2012, physicist Silas Bean proposed that a simulated universe would eventually reveal a finite resolution, appearing as a specific artifact in high-energy physics. This energy threshold, known as the GZK limit, caps the energy of cosmic rays at approximately 5 × 10 to the 19th electron volts. In a simulation framework, this limit acts as a computational resolution, the equivalent of pixelation at the edge of a rendered environment. Within this model, cosmic expansion represents the real-time allocation of computational memory. New space and matter are rendered as the simulation's boundary moves outward. For those seeking a physical container rather than a digital one, the eternal inflation model provides a different structural answer. Research by Alan Guth and Andre Linde suggests that quantum fluctuations can cause space to boil. In this view, inflation is a permanent process that constantly nucleates bubble universes, each expanding within a vast, never-ending sea of inflating space. Both the simulation and multiverse models remain prominent because they preserve a sense of structural order. They allow us to imagine reality as a feature safely contained within a larger, understandable system. String theory expands the container concept into higher dimensions, suggesting that reality requires 11 dimensions to be mathematically consistent. This includes a massive invisible volume called the bulk. The Randall-Sundrum model describes our observable universe as a 3-dimensional membrane, or brain, drifting through this higher dimensional bulk. Cosmic expansion, in this view, is the lateral stretching of that membrane. Alternatively, loop quantum gravity examines the time symmetry of black hole equations. Since the math allows for a singularity to collapse and then reverse, it predicts the existence of white holes, objects that push matter and energy outward. Some physicists hypothesize that our Big Bang may have been a white hole event, representing the bounce of a collapsing star from a previous cosmos. If this hypothesis holds, we are living within the interior geometry of a dying star, expanding into a parent universe we can never see or influence. While simulations, bulks, and parent universes provide the comfort of a stage, the most rigorously tested laws of physics suggest a reality that exists without any container at all. In 1927, Georges Lemaitre derived expanding universe solutions from Einstein's field equations, establishing the first mathematical foundation for a universe in motion. General relativity identifies expansion as the stretching of space itself. Galaxies appear to move away from us because the fabric of the vacuum between them is growing, rather than the galaxies traveling through a pre-existing void. Stephen Hawking famously compared asking what lies outside the universe to asking what lies south of the South Pole. The question assumes the existence of a coordinate that the geometry of the system simply does not provide. In a flat, infinite universe, expansion does not require external room because the universe already occupies all possible space. The process simply increases the measurable distance between points within that infinite field. At the frontier of this expansion lies the pre-geometric void, a phase boundary where the stable dimensions of space and time have not yet formed, leaving only a formless, quantum geometric precursor. The equations of general relativity describe a universe that serves as its own container. It expands into absolute non-existence, surrounded by a mathematically confirmed nothingness. Humanity exists as a localized pocket of order, balancing over a void that offers no walls and no external stage. We appreciate you engaging with these paradigm-shifting concepts across this 2-part series. Of the paradoxes we have explored, from quantum immortality to the containerless void, which one most challenged your understanding of reality? Tell us in the comments. Liking and subscribing helps the channel continue to decode the deepest questions in science. Thank you for watching.